Very good morning. So, we are discussing Unit 3 of Discrete Mathematics subject. So, we had discussed second order linear recurrence relations which are homogeneous. In today's discussion, we will be covering second order linear recurrence relation non-homogeneous. If you remember the homogeneous recurrence relations for second order, this was the general form Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 equal to 0. So, as it is on the right side, as it is 0, we had mentioned it as homogeneous, and then we had said that the general solution will be in the form an equal to ck to the power of n. So, by substituting this, we said there will be different cases, basically three cases. Case 1, if you find the roots k1 and k2 and they are real and distinct, then the solution will be of the form an is equal to ak1 to the power of n plus bk2 to the power of n. The second case is the roots k1 and k2 are real and equal. The solution for that will be an is equal to a plus bn in the bracket k to the power of n. The third case was the two roots k1 and k2 are complex. So, in such case k1 will be equal to p plus iq, k2 will be equal to p minus iq. An solution will be equal to r to the power of n, a cos n theta plus b cos n theta. R will be equal to root of p square plus q square. Theta will be equal to tan inverse of q by p. So, these were the three cases we had discussed. Now, coming to non-homogeneous. When we speak about non-homogeneous recurrence relation, this is a general form Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 plus Cn minus k an minus k is equal to Fn. So, on the right side you will not find the 0, that is why it is non-homogeneous, and as it is of second order, so n is greater than or equal to 2. The general solution for such cases will be an is equal to an h plus an p, where the first part an h is the homogeneous part of the relation and the second part an p is a particular solution of the relation. The first part, homogeneous part, will be derived whatever we discuss in the homogeneous equations. The second part we need to discuss. Now, here there will be different cases, special cases. The first case is, let us say, the function fn is a polynomial of degree q. The function fn is a polynomial of degree q, and 1 is not a root of the characteristics equation. Then that a and p particular solution will be given in the form a0 plus a1n plus a2n square plus aqn cube. If the function fn is a polynomial of degree q and 1 is a root of multiplicity m of the characteristics equation, then a and p will be given as n to the power of m in the bracket a0 plus a1n plus a2n square plus aqn cube. Suppose fn is equal to alpha b to the power of n, where alpha is a constant and b is not a root, then the particular solution is given as a0 b to the power of n. Then suppose b is a root. In the previous case b was not a root. In such a case the solution is a0 nm n to the power of m b to the power of n. Now, let us look at few examples. This is the recurrence relation given, and we know that this is a non-homogeneous recurrence relation of second order. Okay, so n is greater than or equal to 2, and this form is an plus 4an minus 1 plus 4an minus 2 equal to 8. So, on the right side it is not 0, it is a fn function. So, this is a non-homogeneous recurrence relation. Now the general form is Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 equal to Fn. So for this, as it is a non-homogeneous one, what is the solution? The solution is An is equal to ANH, that is the LHS part, that is homogeneous part we have to calculate, and the right side is ANP, that is the particular solution we have to find out. Now what is the solution for homogeneous one? Because we are taking the left part, LHS part, An plus 4An minus 1 plus 4An minus 2 equal to 0. Now this becomes homogeneous. Once it becomes homogeneous, what will be the solution? The solution will be An will be replaced with Ck to the power of n, Ck to the power of n. So we are going to substitute An with Ck to the power of n. So An, instead of An I will be writing Ck to the power of n plus 4Ck to the power of n minus 1 plus 4Ck to the power of n minus 2. Now as it is second order, we will be substituting n with 2. So Ck square plus 4Ck1 plus 4C. So this becomes k square plus 4k plus 4, ignoring c, which is a constant. So rearranging it, we get the two roots k1 and k2 as minus 2. So the roots are real and equal. When the roots are real and equal, we need to check the solution, how it is get. The two roots are real and equal. In such case, the solution is An equal to a plus bn multiplied by k to the power of n. So we'll take this An homogeneous equal to a plus bn k to the power of n. Let us verify it once again. This is a plus bn k to the power of n. Now so a plus bn, value of k is minus 2 to the power of n. Here a and b are the arbitrary constant. Okay, so Fn is 8, right? So as Fn is 8, An Fn is how much? Now here also, initially what we have discussed, different cases. Okay, one of the cases, function Fn is a polynomial of degree q and one is not a root of the characteristic equation. What is the root here? The root is minus 2. As it is not 1, we will be going for this solution. We will still verify it once again. This is the first case. Fn is a polynomial of degree q and 1 is not a root. 1 is not a root. Then we have to use this form, a0 plus a1n plus a2n square plus aqnq. So a0 plus a1n plus a2n square plus aqnq. So we know that this, as it Fn is only 8, so this will be replaced with only a0, rest of the terms will not matter. So ANP particular solution will be a0. So now this value a0 we will be substituting in the given relation. So what is the relation? An plus 4an minus 1 plus 4an minus 2 is equal to 8 for n greater than equal to 2. So an will be replaced with a0, an minus 1 will be replaced again with a0, an minus 2 will be replaced again with a0. So the value of a0 is coming to be 8 by 9. Now this 8 by 9 will be putting, what is the general solution? The general solution is an homogeneous plus an particular. An homogeneous we got as a plus bn minus 2 to the power of n. Verify that. A plus bn minus 2 to the power of n. Wait. Plus 8 by 9. Particular solution we got as 8 by 9. Now in the question it is given a0 is to be equal to 1 and a1 equal to be 2. So both the cases we need to verify when n equal to 0 and n equal to 1. So here n value is 0, so b into 0 will be 0, only a will be remaining, minus 2 to the power of 0 will be 1. So this becomes a multiplied by 1 plus 8 by 9. So a plus 8 by 9. So and when I take n equal to 1, okay, so will be substituting n with 1 and we'll be substituting k with -2. So we'll be getting, after calculation, we'll be getting the value of a as 1 by 9, value of b as -2 by 3. We'll be putting this in our general solution, a plus bn minus 2 to the power of n plus 8 by 9. So value of a is 1 by 9 minus 2 by 3 n minus 2 to the power of n plus 8 by 9. So this is our required solution. We'll take one more example. Solve the recurrence relation an plus 2 minus 10an plus 1 plus 21an is equal to 3n square minus 2. On the right side you can see it is not 0. As it is not 0, you know that this is a non-homogeneous one. This is a non-homogeneous one, second order. Okay. How the general solution is given, an equal to an homogeneous plus a1 particular. So take the left side, LHS, an plus 2 minus 10a n plus 1 plus 21 an equal to 0, this one. So this is of the form cn an plus cn minus 1 an minus 1 plus cn minus 2 an minus 2 equal to 0 for n equal to 1 greater than equal to 2. So as here it is n greater than equal to 0, we will be substituting n with n minus 2. So now that becomes an minus 2 plus 2 minus 10 an minus 2 plus 1 plus 21 an minus 2. So that becomes an minus 10 an minus 1 plus 21 an minus 2 equal to 0. Here cn is 1, cn minus 1 is minus 10, cn minus 2 is 21. So what is the general solution? An equal to ckn. So wherever an is there, you will be substituting that with ckn. So that becomes ckn minus 10 ckn minus 1 plus 21 ckn minus 2 equal to 0. So as it is second order, substitute the value of n equal to 0, 2. So when n equal to 2, so ck square minus 10 ck n minus 1 plus 2, that becomes ck plus 21 ck n minus 2 plus 2, that becomes k to the power of 0. So this becomes k square minus 10k plus 21, because k to the power of 0 is 1. So simplifying this, we will be getting the roots of k1 and k2 as 3 and 7. So they are real and distinct. When they are real and distinct, again the solution is an is equal to ak1n plus bkn2. So k1 is 3 and k2 is 7, and here a and b are the arbitrary constants. What is our function on the right side? Okay, 3n square minus 2. So a and p particularly 3n square minus 2. Now 1 is not a root, so RHS for degree 2, what we get is a0 plus a1 plus a square n square. Putting this in the given relation, what we get is an plus 2 minus 10 an plus 1 plus 21 an is equal to 3n square minus 2. So an plus 2 will be substituted with a0 plus an plus 2 plus a2 n plus 2 square minus 10 an plus 1 will be substituted with a0 plus a1 n plus 1 plus a2 n plus 1 whole square plus 21 a0 plus a1 n plus a2 n square is equal to 3n square minus 2. So that after simplification, what we will be getting is a0 is 47 by 9, a1 is 16 by 3 and a2 is 4, and substituting this in the particular solution, we get 4n square plus 16 by 3n plus 47 by 9. And this is our solution, an homogeneous plus an particular. Substitute that and we will be getting the solution.